All right, so welcome back. Okay, we're going to get started very soon. We'll come back. If you can take your seat, then we'll get started. So next is our opening keynote for the program. It's a great pleasure to have Professor Larry Peterson with us. Actually, for Larry, for folks in networking wireless, he's not someone who needs introduction. But since we have colleagues from other disciplines, let me just say a few words. Maybe just from my own personal experience, right? I think, many of us actually probably grow up intellectually by reading his book, one of the classical book in computer networking. And one thing that Larry did that I look forward to learn more, actually, was that in the past years, he has been leading, I would say, probably one of the most important open source initiatives in networking and wireless in general. So I'm pretty sure we'll hear a lot of insight from his experience. Please welcome Larry.
Thanks. I'm live? Okay, good. I really appreciate the opportunity to talk to you. I've been talking about democratizing 5G for a while now, and since the last time I gave this talk, I added the more. And next time I give it, I'll probably remove the parentheses and make it bold-faced. This is really about lowering barriers so that people can participate in this technology. I'm going to say a few words why I think it's really, really important, an important technology that the research academic community pay attention to. But on a personal level, the application domain hits home. I was raised on a farm in the next state over. The technology has changed considerably. When I was a kid, my dad was really proud of how straight his cornrows were without the aid of GPS. So it's interesting to imagine what will happen next. So anyway, this is about lowering barriers. Oops, let me go here. But this is a really important time and a really important opportunity. And this is a slide that I've been using now for quite a while. And it's really trying to emphasize the importance of what's happening in the transition to 5G and beyond. And so this is the 4G picture. And there was closed proprietary eNode Bs, and there was closed and proprietary mobile cores. And yes, we had the spec, so we knew what was supposed to be inside of that eNode B, but it's really not an accessible technology if it's a 1,000-page standards definition that really only the vendors that wrote the spec understand and are able to reproduce. So it was a really closed system. What's happening with 5G is that we're disaggregating it, and we're taking the radio piece, the analog digital transformation, or moving out to the edge, and we're taking other pieces of that stack and we're moving it into DUs, and we're going to take some pieces and move it back into the central units as well. So disaggregation is definitely happening. The red box is control, and I'm not going to animate this, but the control part of this now can be turned into software-defined networking techniques, and so we can move it out into a controller, and we can run different applications that actually implement the control. So this is really an important opening up of the technology, and it's quite generally now available as open source and, for the most part, microservices. You have to be a little careful about that, because just because it runs in a Docker container doesn't make it a microservice. I'll talk about that a little bit. But this is a really important opportunity. But the way that I like to think about it is what's really happened is that the boundary between the cloud and the access network has moved. And so now everything that we understand about the cloud, which is all about feature velocity, is available to us in the access network right out to the very, very edge. And it's available as open source. But as I indicated in my title slide, that's not enough. So what I want to talk about for the next few minutes is what the challenges are and what we're trying to do about that, and how you can get involved in it. And that kind of all gets wrapped up in an open source project called Ether. The other thing I need to say about that previous slide was, just because the cloud consumed the access network doesn't really tell you anything about location. But what I would like to focus on is the very, very edge. So the cloud is not back in the data center the cloud is now at the edge. And by the edge, I mean in your enterprise or in your physical plant, wherever that might be. So this is a project, the Linux Foundation, and that's actually new news. Just a little bit of history. Ether is 5G platform designed for edge clouds, and it's made up of a bunch of components. One component is an SD-RAN, and in particular, the software-defined networking aspects of that with a near real-time RIC. And that's compliant with ORAN. The other part of it is a mobile core, which we call SD core. So SD-RAN and SD core are the two major components. Those are both Kubernetes workloads. They collectively, though, you can put them together and they provide you with an end-to-end private 5G platform. And that includes all of the management and operational pieces you need, which is an essential element of actually having a private 5G solution. Now the history is that this was built at the Open Networking Foundation, ONF, which you may know as a place that did open source platforms for software-defined networking. And what we discovered over the years working with telcos primarily, AT&T was one of our big benefactors, was that they were mostly interested not in backbones, but in access networks. And so the SDN work that we did for many years, software-defined networking, was really focused first on fiber to the home and then on the mobile wireless network. And that eventually turned into Ether. This was a lot of work funded over the years in SDN generally by the telcos and network operators and some cloud companies like Google. But at the end, when we were really pushing the private 5G in Ether, it was funded by a Department of Defense contract. DARPA wanted an open source end-to-end 5G solution. And that's essentially what we built with an engineering team at the ONF. We had a 30-person engineering team. I don't have it in my slide, but what you may know about is that ONF was acquired by Intel, which as a nonprofit open source is a little weird, but what that meant is that the engineering team all went to Intel and left behind all the open source code. And that's actually the next little bit of this. That pile of code then moved under the umbrella of the Linux Foundation in February. And as a process, we transitioned from a managed service to a deployable platform. So during the time that it was at ONF for whatever, 3-4 years there, we were running an operational, there was no agreement and there were no money changing hands and there were no service agreements being signed. But we tried to make it as operational as possible, and we had a set of universities and other research sites, not unlike what's happening in the test beds here. And we ran this on a day-to-day basis. And so that's an important part of all of this. But the takeaway from this slide is what happened, which you go back to my title, it's open source and more. We had a $30 million investment in a pretty good private 5G solution that was abandoned by the engineers that implemented it. And that we had a whole bunch of GitHub repos filled with really good code that no one knew how to use and could take advantage of. And so that's what we've spent the last couple of years doing, and now we're getting pretty good traction with that. So just a little bit about Ether's DNA. When we started this, we had a very much a cloud mindset. We were using all best practices in cloud DevOps and DevOps in particular, and we wanted to build a managed service. So nowhere in our language do we use the word BSS or OSS. We're building a managed cloud service. We do have telco DNA. We were working originally with telcos. And so we are paying attention to the standards because we do want this to be 3GPP and ORAN compliant, and it is. But we also then were targeting the very, very edge, and to us that was to put this into the enterprise. So private 5G. And the edge piece is important because we have local breakout. Everything can stay on-prem. If you want to take some of the control plane and move it back into the cloud, into a data center, that works too. But everything can run on the edge, and in particular, the data path or the user plane all runs on-premises. Your data never has to leave your site. So Ether is kind of at the intersection of those worldviews, and believe me, those are three very, very different worldviews. And so it's a little bit challenging to reconcile those. So here's the block diagram. That is an edge cloud, so imagine it runs on your campus or in your plant. It is based on open source cloud native tooling, so Kubernetes, Helm, and the like. There's two workloads that we deploy, SD-RAN and SD-Core, which I'll talk about a little bit more in a minute. There is a management plane that sits on top of that because you have to interact with this thing. I'm showing a little portal up here, but that could be programmatic as well. So you have to operate it. Users have to be able to come to this and turn things on and off and speed them up and slow them down and so on. And then the final piece, I'm calling it lifecycle management. I guess I labeled it on-ramp is the name of the component there. But it's all about how do you manage this software over time because it will change. And so those are the main pieces. And as I indicated, for quite a while, we ran this as an operational test bed. And I'm showing a set of sites, and you can kind of see maybe a little bit. There's Google, that's where Google Cloud, that's where we actually put the control plane, and the as a managed service, connectivity as a service lived up there. One of the sites that was operational for quite a while was in Berlin, and if you may be aware that Deutsche Telekom ran a plug fest for a couple of years where they were bringing in different RAN technologies and plugging them all together. I'm going to put up a slide. It's extremely busy, and just take away the busyness of it is that when you have one of these things, you're having to interoperate with a lot of different partners, and the core that I talked about was in there, the RAN was in there, different people were bringing applications to run on top of it. We were running both 4G and 5G. And so this whole box here is the O-RAN component. So again, very busy slide, but that's just to say that these pieces were all put through the ringer in terms of interoperating with different partners. So let me drill down for just a minute into each one of these components to give you a sense of what's there. And that'll give me an opportunity to talk about what's really kind of hard about this, more than just having a repo with some software in it. So SD-Core is a cloud-native, horizontally scalable mobile core, 3GPP compliant. There's both a 5G control plane and a 4G control plane, and they both share a common user plane that will then speak either the 4G or 5G interface to the devices and to the radios. We're mostly focused on 5G. The 4G is still there. You can still make it work. It still runs, but the emphasis has certainly shifted to the 5G case. Now, what's really unique about this particular Ether core is, I think this is where my animations come in, is that it is in fact horizontally scalable. As far as I know, this is the first time it's been demonstrated that you can scale the control plane. And why you would scale the control plane is because you have a scalable number of devices that are trying to connect to it because you have an IoT application. And being able to do that at low latency in predictable time is not that easy. And so without abandoning the modularity of a microservice-based solution, we now have a scalable version of this as well. So again, that's a workload that we deploy at the edge. And again, the control plane we could deploy in the cloud, and you could deploy the user plane at the edge if you wanted to. So the RAN, when I say SD-RAN, it's really a near real-time RIC. And here we turned to the technology that we developed at ONF to manage switches, software-defined networking, and we built an ONOS. Maybe some of you have used it. It's an open network operating system to control Ethernet devices, but you can also control RAN devices. And so we started with that, and we just built in all the schema and models and so on so that we were now controlling the RAN devices instead of wired devices. And you can run a set of applications on top of that. And importantly, it speaks the O-RAN E2 interface out the bottom so that you can talk to all of those devices. Something that's happened is that there are a set of service, if you're aware of it, there are service models defined to both read and write that control information that SD-RAN supports. So again, this is just a microservice-based workload that you can load onto a Kubernetes cluster. Now looking at the box that sits on top of that, there's a management plane. This is a runtime management plane, and the role it plays is that it gives you the ability to do closed loop control of this service. So again, I think of it as this is a managed cloud service. So what is that service? It's connectivity as a service. What do you do with connectivity? Well, you add devices to it, you add applications to it, you set up slices or connections between them, you assign QoS properties to those connections. Those are all the kinds of operations that you can perform, and you can aggregate things together so it's easier for you. There's a portal you can do that at, or you can use a programmatic interface, and you can read and write data about the behavior of the network, and then you can control it. And now, what are those applications? Well, there have been a number of them done. Generally, people are tending to use machine learning there. So Intel Labs is one of our partners, and they have used their machine learning open source tool to build applications. Another one that's happening right now is something we call Smart 5G, but that's basically watching power usage and turning off base stations, turning power up and down on various subsystems based upon power usage to control the power the energy that's being used. So that's just an illustrative example. So dropping down into that runtime control system just for a minute, because it's actually a pretty important component. What you're basically doing is, this is not set this up at configuration time. This is, if you're going to use it, it's going to have to run operationally 24/7 forever. And so you are making changes to the state of the system, not by downloading a new config file and restarting everything, but just by at runtime loading in a new state, but you have to remember that state. So it's a combination of an API and persistent operational state that you're maintaining. And again, we turned to some technology that we had. We had already had state to control switches. In fact, I'm showing a set of backend components here. As originally defined, Ether included an SDN controlled fabric. So you built a cluster of servers, and the backplane for that cluster was SDN controlled. That's no longer included as part of Ether, but that sort of motivated this, that there's an interface for controlling devices. What if we just use that interface to control services like you control devices? And that's basically what we've done. And so you feed a model of a schema, if you will, for all of the things that you want to do to those devices. You can then use that model to generate an API, and that API then controls this config module, which has persistent state. And you got to adapt because these other services don't speak GNMI, but that's fine. You just write an adapter. So this is now the runtime operational control system for Ether. Non-trivial, but a critical part of it, because this is how you give all the different stakeholders the ability to control this thing at runtime. Okay, finally I want to get to lifecycle management, and this is where things got really hard. So like I said, the engineers all went away, and they left behind a pile of code that they were the devs, but they were also the ops. And they were the only ones that knew how to configure this thing and set it up in the first place. And back when it was an operational network, it took interaction between them and the local site to bring up a site. It wasn't just a trivial thing to do. But a whole lot of know-how disappeared at that moment. And if you go start digging through the code, well, it's just a matter of looking through the code. Well, it gets kind of hard. So what I'm going to describe now is this vertical system over here called OnRamp. It's called OnRamp because it helps you on-ramp to get Ether up and running. So the configuration challenge has multiple parts. Are you familiar with Helm? Anyone? Not too many. Okay, so Helm is just a specification that you hand to Kubernetes that says, these are all the containers I want you to bring up. And these are the parameters to give all of them. So it's a configuration, it's a YAML file. And based upon that YAML file, I spin up SD core. Based on another YAML file, I spin up SD RAN. Well, that's trying to understand how that worked, you'd have to pour through a 800 lines of YAML to try to figure that out. just chock full of configuration variables that make absolutely no sense to you because they're not well documented. They were just in the brains of the engineers. That's to bring up the control plane, another 135 lines of code to bring up the user plane. So you got to know how to set all those variables, not necessarily easy. Then you got to configure the G-Node B. And this is just a cut out of the user's manual for the G-Node B. And I can't even read it to you. It's just telling you a computation you have to make to configure a particular parameter, this particular parameter in the G-Node B, so that you've partitioned out the spectrum in the right way. All right, so that's complicated too. It has some default settings, and you can bring it up the first time, and it actually works okay. But then you realize when you turn the back of your G-Node B over that it really only worked for bandwidth B48. And if in the US, you may have remembered that little skirmish between the FCC and the FAA over the use of a bit of frequency near airports. B48 was originally included, kind of nudged up a little too close to what the airlines were using. So this was the first G-Node B I had, and I got it to work, and then I got another G-Node B and it didn't work, and it was all because this number had changed, and it became a band 77, I think, which brought you back a little bit further away from interfering with airplanes landing. But in any case, you got to know about that stuff, and you got to know that the phone that you bought has supports the right bands as well. And those are just 3 examples. If you look across the end-to-end spectrum, it's just an absolute configuration nightmare. And you have to configure all of these little pieces in a consistent way. And so I've kind of called out a few examples here. You've got to get all the PLMN code that identifies which carrier you are. You've got to get the ISMEs consistent. You even have to program the SIM cards. And it never occurred to me, I think of a SIM card, it's got my phone number on it. Well, and it's also got this unique identifier. No, it's an entire database. I didn't realize this until you crack one open. And this is just all the configuration that you have to do in the 5G space. There's a whole nother SIM space, and I don't know if you can read any of those, but imagine all the vendors who wanted to support 5G devices got together and did the union of all the things they did differently, and then they put that into this database. That's essentially what it is. And to get a particular radio to work with a particular phone, to work with a particular core, you've got to make sure you've got all of those set up in a consistent way. And you don't necessarily support all of the components because that was something that Nokia put in it, and I don't have it in mine, or whatever. All right, so it's a configuration. Hopefully I've convinced you without jumping into the code, which I'll do if you're not convinced, that this is a configuration nightmare. And that's just to get all the components individually set up. The other thing you have to do is you have to then deploy that into some hardware, into some servers. And here it's like, so the outer box is just a server, just a Linux box. And the UPF is the container, or it's a pod that implements the user plane. And it's going to be connected through an Ethernet port to the radio on one end. And maybe I've got 2 different Ethernet ports, but even if I only have one, then it connects off to the internet in the other direction. What could be easier? Well, it's not so easy simply because that UPF implementation is inside of a Kubernetes cluster. Kubernetes was really good for having a little world that I could do parallel computing in, and distributed computing, but it doesn't speak to the outside world so well. And this is all about speaking to the outside world. And so, you have to add some more Linux bridges in there. And the next thing you know, they've all got their own unique IP subnet. And long story short, it's really a challenge. I'm just for illustrative purposes giving you all the TCP dumps you do to see that packets made it all the way through going this way and then all the way coming back. And way out here, I'm giving you an IP address space for all of my UEs, but that has to be NATed, so there's NATing going on as well. So I hadn't thought about it ahead of time, but what you're basically doing is you're implementing an IP router in an overlay. and embedding that IP router inside of a Kubernetes cluster. And that combination makes this really challenging. This is the single hardest thing for people to figure out and debug when they're trying to bring Ether up. Okay, so I've now hopefully convinced you that this is a challenge. And literally what was happening with Ether is we had this wonderful pile of code, and people kept coming and trying it, and there was some documentation. They kept coming and trying it, and then leaving it away, going away, and probably never coming back again because it was just too hard. And so what we did was we re-engineered the lifecycle management piece over the last couple of years to try to make this now consumable open source software. So this is just a fairly simple picture of the lifecycle management pipeline that we work with. And it's you've got code that gets checked in by developers. It gets integrated, and you produce some artifacts like Docker images. And an operator comes along and gives some configuration code, and then you deploy it out into this cloud based upon what the configuration said, which artifacts to deploy where. And the original version of this, and that operational cloud is Ether, and the original version of this was built with all open source. Again, everything's open source. It's not like there are any secrets here. The secret is just in how obscure the various combinations are. And I don't know if you recognize any of these open source projects, but the really critical ones over here were Rancher and Terraform. Were able to distribute this code containers out to everywhere it needed to go. So at one time, we had an ops team here, and they were a crackerjack ops team. And they knew how all of this worked because they built it. But imagine you are here, and now what are you going to do? And the answer is, well, we threw away a whole bunch. The other thing is, you want to now deploy this for your own purposes. You go, I have an application, I have a local edge site, I'd like to bring this up and try this out. So you want your version of Ether as opposed to that general one that was deployed before. Well, what we ended up doing was replacing this pretty complex configuration information, which really is probably necessary for a full, truly global deployment, with a pretty simple tool, Ansible, if you happen to have used it before. It's a pretty simple, straightforward tool. And then we just happen to configure that in a way, and we just call it on-ramp. It's just a set of playbooks to do the deployment. Still taking the same artifacts that were produced by the continuous integration piece, and then deploying them onto your cloud, your local edge cloud. So the idea of on-ramp was it was about transitioning Ether from being a managed service to a deployable platform that anybody could deploy. And they would want to deploy it for all the reasons that we talk about in gatherings like this. It includes all the tooling so that it's a managed service once you get it deployed. You now have a portal that you can log into and you can control it. But the goal of this was to help users own the configuration. Now I'm getting into the meat of it. The word ownership and to own is absolutely critical and important to this way of thinking. And we had a large target audience. We were trying to do it for the purpose of education, but you could own it for research. You could own it because you wanted to take it off and provide a service for real. And there have been people doing that across that entire spectrum. It has to be defined then for different target environments and feature sets. I care about the core, I don't care about the RAN. I just need enough RAN to drive the core, or vice versa. Or I only care about applications, so just do the obvious thing down below. So it's different combinations that you want to support. So for example, you can bring it all up in a single server, and you can have them physical or emulated GNodeBs. You can bring it up in a cluster because you are interested in issues of scale. And again, you can emulate or have physical GNodeBs. You do it in a single site, or you could do multiple sites. We haven't done the multi-site one yet. Originally it worked there, but we haven't done that particular one yet. So these deployments are called blueprints. And we start with quick start, and we ramp it all the way up to an entire cluster that you could do a field deployment of. So I want to just real quickly give you a sense of these and then get to the punchline in a moment. So quick start. I ought to be able to bring this up on my laptop. So you create a VM, you download the code, you type make, you can build it, and you can run it with a simulated G-Node B. GNB Sim is a really, really nice simulator that was part of this whole effort that really stress tests the 5G control plane. Not so much the data plane, but the control plane. It all runs inside of a single server. Actually, if it's a shaded box, it means it's actually Kubernetes. So we bring up Kubernetes on a single server, and then we run this workload in it. You could scale the cluster, and you can pull the G-Node B Sim out and put it in another server or a scalable set of servers because you wanted to scale the workload. So scale is an important factor here. We want to be able to test that as well. Instead of simulated, you can connect it to a commercial G-Node B. We've gotten Mosel Labs Canopy 5. This used to be Seracom. Mosel Lab is the subsidiary that's doing private 5G in the US. This happens to be an indoor switch. We're working with the ESNet, and they're doing outdoor switches because they want to do field tests there. But that's a possibility. We just recently, thanks to collaboration with folks here, got it to work with the OAI RAN blueprint. And what's my last one? Oh, you can also bring up the entirety of SD-RAN. So SD-RAN, again, it's running in Kubernetes. It's a scalable workload as well. In this particular case, we ran it with another simulator called RANSim. What the next step is that we're this close to is getting SD-RAN with the OAI radios, and then we will have an open source near real-time RIC controlling a software-defined radio. So here's the takeaway. Why were there so many blueprints? Because there isn't an obvious single linear progression of things you want to do. Some people are interested in this, some people are interested in that. There was not an Uber one blueprint for all. And I think a lot of times people assume that there is, but there really isn't. And so what we do is you start with quick start, and then you test it under control of the runtime interface, and then you attach a physical G-Node B, and then you scale out the cluster. And all of these are just learning lessons that you learn about the dimensions of configurability. Then you set up multiple slices so I can separate this traffic from that traffic. At the end of the day, you take ownership, and that was what this was all about. And then you do whatever you want to with it. And if you do something interesting and you create a new blueprint, we would definitely like to have that back and make it available to other folks. So this is maybe a little controversial, but you often hear, with a single click, you can do this wonderful thing. I don't believe in single clicks. It really implies that you had picked exactly one solution and you'd gotten it to work, but you had not given any ownership to the person that did that single click. They don't know anything more than clicking a button. That you really have to expose, not necessarily at once, all of the complexity, but you have to incrementally expose people to these are the dimensions that are available to you to control. Here's an initial set of settings. If this is a direction you care about, then now you're prepared to go work with it. So let me pull this all together with a couple of conclusions. And hopefully this will be relevant to the activities in this project. Oh, I'm sorry. I got one more slide before I get to that. The way that we accomplished this incrementalness is simply that we layered the config information. And so, whereas before I was talking about all those Helm charts with all those lines of code, we have an overlay on top of that, which is much, much shorter. So to deploy a 5G radio blueprint, it's a fewer lines of code, and they're the ones that are relevant to the 5G deployment. But on top of that layer then is at the very top is sort of the umbrella statement of what it is you want configured. And those are actually quite readable and manageable. It's a very few number of configuration variables you have to change. Okay, now let me get to the takeaways. Network operations, network management is a barrier to adoption. And it is unusually complex for 5G. And I could go on a rant here. I will do a very brief rant, which is the 3G, 4G, 5G has all been under the control of network operators. Their business is to operate. They have absolutely no motivation to make it easier for anybody else to operate because they've got the monopoly on the expertise to do that. So the development of this entire technology, never once was it thought, how do I make this easier for anyone else to operate or deploy and democratize and take ownership of? We have to figure out how to manage that problem, or all we will be doing is research that will then feed back into the existing model of how this is all commercialized. So that's point one. Point two is hands-on experience with at least some operational capability is absolutely critical in my view. And these are my own biases, but to run something on day one and then day two and day three with a user doing something unexpected is how you learn what the real problems are. Otherwise, someone else is telling you what those problems are, which is fine. That's a way to make progress, but seeing that you tried to do something and how it broke down, or how some user did some crazy thing, is really how or how the technology behaved in an unexpected way is really how you discover where the interesting problems are. So operating a system is a great way to expose the next research challenge. And if you make a contribution very narrowly in some subsystem, the only way broadly others can take advantage of that contribution is if you also send that contribution back with the little hooks in the operational system that are necessary for people to use that. An obscure config file is not such a hook. You have to really plug it back into the framework that exists. And finally, that there are limits to automation. Supporting a fixed set of predefined scenarios is a good thing, but then people are going to want to customize those. And the moment they start customizing it, they have to take ownership of it. And the only way to take ownership of it is to be exposed to all of the degrees of freedom that you have and the complexities of those degrees of freedom, but exposed incrementally. And that requires education, training, documentation, and lots of other things that go, just the know-how that goes into that. Now, it's not just, in my view, about operating this thing, and that's not research. First of all, I think it's how you discover research, but there's a really interesting research problem in here as well. If you really stand back from this, it reduces to a state management problem that's complicated by the fact that there's different stakeholders. Just to reduce it to its simplest possible terms, an engineer who's trying to test a component they build will put together a configuration that tests that component, but that configuration spec has absolutely nothing to do with the way you're going to want to deploy it. And so there are no incentives on the engineering side that necessarily carry over onto the operational side. And we have to figure out ways to seamlessly move from development time by engineers to deployment time by operators to runtime by users, because that's all part of the larger equation. And so now what is there? Well, there's a pile of code, a new pile of code on ramp, set of blueprints. There's a pretty substantial guide, set of documentation to tell you how to use it so that you can bring up your own 5G platform on your own, using your own radios, whatever they might be. It's an active open source project. Like I said, it's under the Linux Foundation, but it's a self-contained project, just like all the other projects are under the Linux Foundation, like Kubernetes or any of the others. There's a wiki, and you can get started there. There are TST calls weekly. You can get involved there. But starting with the wiki is a good way to figure out where all these other things are. All the code is on GitHub. OnRamp is in an old organization that came out of ONF's predecessor, which is Open Networking Lab. SD-Core and SD-RAN are both in different organizations. That's fine. The repos are all pretty self-explanatory once you get there. And finally, there's a set of educational material that Bruce Davey and I, who wrote that book many, many years ago, have now turned our attention to emerging technologies and how we can document those so that people can understand them. So I think with that, let me stop and see if there are any questions.
Get the question started. So do you have, let's say if we want to teach a course in 5G or embed that experience as a part of the maybe a 4-semester course, any advice on how to best approach that? Do you think the process you mentioned that could be a model to follow or something else?
Well, so I guess the best I could say is I would say to the professor, follow the documentation there and incrementally make as much progress as is important to you. And Jim Croce has done that. Jim is wrote the other networking textbook. So Jim was teaching a 5G class and went through this whole process. The thing that's not here is the exercises. And so I show you how to do a packet trace, but I don't do a packet trace for you and then teach you, we'll look at what the packet flow was. Right, so there's another level to just beyond this, that this would be a starter for that would turn this into a course. And that would be really great to do that. Yeah, turning the available things into exercises.
Thank you.
Dr. Peterson, awesome talk. My name is Christopher Stewart. I'm a professor at Ohio State. Maybe first I just want to commiserate your description of dealing with Helm, Docker, and Kubernetes. Oh, yes, you just talk on forever about that, brother. My question is about sort of the intellectual solution, right? So if I can see how this model works for an individual project, right? And obviously, talking about 5G, it's a very important individual project, and so, maybe it just works here and that's all we need. But for instance, for myself and others that are struggling with that same level of complexity for other things, for instance, in the space of digital agriculture, which we'll talk about here, this solution doesn't seem to get at the core problem, which is that the operations people left and then someone had to learn all of this over again. So it feels like it would be hard to have educational material in every use case.
It's a difficult step, but a necessary step. Otherwise, we will always be beholden to those that know how to operate. So this is not trivially reproducible. Absolutely right. You have to have the resources and the people that are interested in figuring out how it worked and then documenting that, right? And then a little bit of tooling. This particular case, the choice of Ansible happened to be because a student at Purdue that I started to work with had been using Ansible to set up Ether for his own research purposes. All right, and then I appreciated what he had done, and we've been building on that. So yeah, it takes a little tooling, it takes a lot of documentation, and it takes time, resources, people to do that. But either you don't get the, another way, so let me say it another way. Operating these things is a first-class problem, and it needs to be dealt with as much as understanding the internals of the code or whatever the domain-specific thing was. Yeah. Now, eventually, the operational tooling, I hope, matures enough that it's easier to do that. But yeah, that'll be a ways.
Hello, great talk. I have several questions, but I'm going to limit them to only probably one or two. So did your, this is one particular approach, right? To make this open source, the whole complexity becoming, 5G compatible, all of that. So probably your code, this code is, implements release 18, something like that. And how do you see how difficult is going to be when you go to release 19, 20? How do you, when you say scalable, is this scalable with respect to releases? So
that's an orthogonal question to operating it. So now each one of these projects need to track advances. So on the SD core, the upgrade to 18 is underway, and that depends, release 18, I'm sorry, yeah, 18. That depends on having a collection, a community of developers. You don't have the developers, not going to happen. But they have a path that they believe, and it's not a large team, to get to 18. So if you don't have that, then you will stagnate. Yeah, there's no easy answer to that. Hopefully, though, the more people, the whole point of lowering the barrier to adoption was to get more people vested in it so that that community would grow. And it's a little different, I'm sorry, I'll hijack this. It's a little different than, say, Kubernetes or Linux, where you're contributing to a platform that you use. This is now the interesting level, so to speak. And so there's so much commercial activity going on there that the motivation isn't quite the same as contributing to Linux.
I'm just going to have a follow-up question, sort of follow-up question. As research community looks at AI and trying to use AI for networking to improve networking, and obviously they are looking at ways to validate the algorithms, how 5G would work, et cetera, with those approaches. Does this open source make that easier? Do you have enough hooks in the code or thinking that would make this sort of AI compatible or somehow native, AI native, et cetera? Thank you.
Yeah, I didn't show this slide, but yeah, that smart 5G is all about figuring out what the right APIs are. Oops, I guess you can't see it. Well, it doesn't matter. I just took it. I've got a beautiful slide here, I'll show you. But it's basically about, so there are a set of APIs there now. It's what do I need to do to grow that set so that I've exposed the right information?
Yeah, my name is Myra Cohn. I'm at Iowa State University. And so this problem of configurability you're talking about happens across many, many different domains. I'm just curious if you have thought about a global view and looking at modeling what's happening in this configuration space and leveraging, so you have users who are individually finding that configurations work, but you have an exponential space, and every time somebody adds a new option, it grows. And so have you looked at sort of the global view and leveraged what you've learned from people, and you can even do processing in the background and sample that space and model it. So I think there's a lot of opportunities here to do something.
Yeah, great question. I think where that actually comes into play from my experiences in the runtime interfaces and the runtime operation, and that there's an API. And to my view, the key to that API is that it is in fact all model-based. So now if I, through an open source group that a TST says we are now willing to make this change to the API, it's a change, here's how you do it. Just change this model, generate the API. So model-based or model-driven makes that process much more manageable.
Okay, thank you.
Thanks. I know Ranveer and Monisha are waiting for us online. Thanks for doing that. But if I may just one more question, I feel that this could be useful and for the broader community, right? I think we know that I guess academics have been contributing to open source, participating in many ways, definitely as users for sure. Also, there's I guess some emerging initiative, for example, from TIP, right, the POSE program, try to also encourage academia to think about what else can we do for open source. I'm wondering, since you have gone through that, through your own rich experience, any advice about, for academic folks who want to potentially even pursue this route, not just as a user or individual contributor, but trying to nurture a community around open source? Any advice you would have for folks?
Yeah,
who may not have such experience already.
It's a tricky thing to do. Mm-hmm. It has to be the right time and the right technology. You can say I'm going to open source this and build an ecosystem, but if it's not the right time and the right interest, it'll be very difficult to do. I mean, I think there's a lot of opportunity in this specific space. One of the things that's tricky about it is we're competing with each other in the research space or in the commercial space, and you have to have something that everyone's willing to contribute to contribute back to that doesn't hamper their research. So a student does, the parallel, the scalability stuff that I showed you here is a student at Purdue did that. He's still got to get the paper published, but he's hopefully about to do that. And then he contributes, he's willing to contribute that back and people can build on it. But if you don't contribute it back because you're not motivated to do it, or you're even concerned about doing it, and I'm picking on researchers here, but the commercial world is way bad. They'll take the code and we'll never see it or hear from them again. I wish I had a better answer, but certainly you have to make it easy to use. You have to do a lot of the groundwork that's not obvious and like you're doing here. There's a lot of hard work and there's no simple answer to that.
Thank you. All right, let's thank Larry again. If you don't mind, we'll catch. Larry will be around until tomorrow.
Yeah, I'm here the whole time.
Yeah.
Yep.
Okay. All right. So thanks, Larry again.